Okay, so we are now starting Redox. This first lesson is basically just going to introduce you to a couple of new things and review a few things. So first thing to quickly go over is just your types of reactions. Okay, you're going to find that eventually the further we get into Redox, we're not really going to worry so much about that, but definitely the first couple of videos you're going to find that our prediction of products is really going to rely on our types of reactions. Okay, you're also going to find as we go further into the unit that out of the 6 kind of general types of reactions that we've talked about for the last couple of years, there are a few of them that never qualify as being redox reactions. Okay, so really quickly, the ones you want to remember, right? We've talked about formation, so that's an element plus an element to give you a compound. Decomposition, so that would be the opposite. We have a compound breaking down into elements. Single replacement, so we have an element plus a compound. We're making a new element, a new compound. Double replacement, right? We have 2 compounds. We switch the partners to make 2 new compounds. Neutralization, which is technically a subset of double replacement. It's just specific to acid plus base to give us water and that ionic salt. And then we have complete combustion, and that is where we combine our hydrocarbon with oxygen to produce CO2 and water, okay? So those are going to be helpful as you start working through some of the first couple of pages of your work booklet. You are going to see that you're going to have to make use of that at some points, okay? All right, so other thing to review from Chem 20 would be your net ionic equations, okay? If you remember back to last year when we worked on net ionic equations, we talked about 3 kind of general steps. So the first step was to write your complete balanced equation, making sure that you include all of your states. The second step was to write your total ionic equation. So this is where we looked at that complete balanced, and anything that was aqueous and ionic, we broke apart into individual ions because obviously we know that ionic compounds in solution dissociate and exist as individual ions. Okay, we did the same thing for strong acids because, again, we also know that strong acids undergo complete ionization in solution, but we did not do that for weak acids. We also don't do that for things that are solids, liquids, or gases. Once we had generated our total ionic equation, we then checked for spectator ions, right? So remember, spectators are those ions that don't change. So they are identical on the reactant side and the product side. We then canceled those out, and that then left us with our net ionic equation. So if we look at this example, we have barium nitrate plus sodium sulfate. So this is going to be a double replacement reaction because we have a compound plus a compound. So we are going to make sodium nitrate. Okay, it's important that we are checking our states. So we go to our solubility table, this is aqueous. And then our other product is going to be barium sulfate, which I want to say is solid, but I'll give it a quick check. And it is. Okay, balancing wise, we need a 2 over here, right? So that was step 1, write the complete balanced chemical equation. So step 2 is that total ionic equation, and this is where we look at our original equation and anything that was aqueous and ionic, which in this case is the barium nitrate, the sodium sulfate, the sodium nitrate, we're going to break apart into individual ions. Anything that isn't, we're going to leave alone. So this barium sulfate, because it was a solid, we're not going to touch it, okay? So we're going to have a barium ion, hitting the wrong buttons. So Ba2 plus AQ, we're going to make 2 nitrates, which are aqueous. We are going to make 2 sodiums, also aqueous, and a sulfate. Okay, so these are all aqueous down here because they came from aqueous things up here, right? That's where that state is coming from. The charges are coming from our periodic table or our polyatomic ion table. The coefficient in front represents at this stage, because these first 2 were balanced with 1s, just represents if there were any little subscripts, right? If you remember back to last year, we talked about how we generally don't have subscripts. The only exceptions to that are polyatomics, right? So the nitrate got to keep its 3, the sulfate got to keep its 4. So that's our reactants. Now we move to our products. So we had 2 sodium nitrates. So in this case, because I had the 2 in front, I have to make sure that I apply that to both the sodium and the nitrate. Okay, if one of these had an additional subscript, then I would have to multiply those 2, but in this case they don't. So I would have 2 sodium ions and then 2 nitrate ions. Okay, and then that barium sulfate, because it was a solid, we're just going to leave it alone. So we're literally just going to write it exactly the same way that it appeared in that first line. Although, of course, my font is kind of big, so it did that. Let me just make it a little smaller so that it all stays on that same line. Okay, so we broke apart everything that was aqueous and ionic. We left the solid alone, right? Solid, liquid, gas, we don't touch them. Those stay the same. Now, to write our net ionic equation, we need to figure out what our spectators are, right? So spectators are always going to be ions. So we're checking to see if we have identicals on both sides. So here's Ba2 plus Aq. Over here, I don't have a Ba2 plus Aq, right? I have barium, but it's not identical. Therefore, I can't cancel the barium. I have 2NO3 minus. I have 2NO3 minus, so I can cancel those because nothing about those changed. They were completely identical, so they were a spectator. Same deal with the sodium. They're completely identical. They have the same balancing number, the same charge, the same state. The sulfate I can't cancel because same as the barium, it looks different on the other side. Okay, and now what we're left with, once we cancel out those spectators, is going to be our net ionic equation. So we get the Ba2 plus Aq plus the sulfate. And one of these days I will figure out what I'm pressing. And that is going to give us that BaSO4 solid. Okay, so the further we go in the unit, you're going to find you're going to become much more comfortable writing net ionic equations. You're also going to find the further we go in the unit where you are going to start using a table in our data booklet significantly more, and that's going to kind of immediately eliminate those spectators from our equation. Because really, when we're in redox, we're always going to have some spectators, and we're not really interested that much in the spectators because they don't do anything, nothing about them changes. We're really more interested in that net ionic equation, okay? So important to make sure that you kind of have the skills to be able to generate a net ionic equation. Some of you may find that you're like, I have to write every single step out. Some of you may find, especially after you practice enough, that you're like, you know what, I don't need to write every single step out. I can kind of recognize from the get-go what my spectators are going to be, because there are definitely some common spectators, right? Group 1 ions, pretty much always going to wind up being a spectator. They're always soluble. You'll also see as we go further in this unit that they're not very reactive as ions. So yeah, they tend to kind of generally be spectators for us, okay? Okay, so now looking at something a little bit new, right? Those first 2 slides were things that you are familiar with from Chem 20. Now we're going to start looking at writing half reactions. So the reason we write half reactions is because this unit is called redox, and it's called redox because we're looking at reduction and oxidation, and basically that involves the transfer of electrons. So if you look here, it says oxidation is the loss of electrons, okay? And reduction is the gain of electrons. So we often use the saying, Leo the lion says grr. Okay, so we use the saying, Leo the lion says grr, where Leo, loss electrons, oxidation, and grr, gain electrons, reduction. So definitely you need to be able to recognize when you have oxidation versus when you have reduction. You're going to find when it comes to redox, although there definitely is quite a bit of like logic and problem solving to it, there is also definitely some memorization pieces. Okay, this is why redox tends to be either a unit that you do super well in or a unit that you really struggle in. And that's because if you just can't get some of these kind of foundational pieces nailed down, every time you look at something new, you're kind of like, I don't know what's happening. What is this? What is that? So definitely some of the memorization pieces, I guess I would say, is being able to recognize when you have oxidation and when you have reduction. So really important to know that in oxidation you are losing electrons, and in reduction you are gaining those electrons. So what we do to be able to recognize an oxidation and recognize a reduction, because they always go together. We can't just have one without the other. That's why we call them redox reactions. And that's because one of our species is going to go under oxidation and the other one is going to undergo reduction. We can't have both oxidizing or both reducing, because those electrons have to come from somewhere and they have to be going somewhere, right? So where they're coming from is whatever was oxidized. It's losing those electrons. Those electrons that they lose then are being gained in our reduction half reaction, okay? So when we are doing half reactions, what we basically do is we take an equation, like the one down here, that Mg plus Br2 to give us MgBr2, and we split it into two halves. So how we split it into two halves is we split it by the type of element. So in this case, we have Mg and Br. So one of our half reactions is going to show the magnesium, and the other half reaction is going to show the bromine. So we're going to have magnesium turning into, and although this is an ionic compound, right, we kind of just talked about net ionic equations so that we can recognize this is really a magnesium ion. Okay, our other half reaction is going to involve that bromine, right, because that's what we had on the reactant side, turning into those two bromide ions. Okay, so we're splitting by the type of element. So the magnesium that was on the reactant side is still on the reactant side. The Br2 that was on the reactant side is still on the reactant side. They're just in two separate things. We then looked at magnesium bromide. We recognize that this is an ionic compound, which means really it consists of magnesium ions, which is why we put Mg2 plus in this equation, and two bromide ions, which is why we put 2Br minus in this equation. So when we look at these two half reactions, right now you should find that your elements are balanced, right? So I have one magnesium and one magnesium. I have two bromines and I have two bromines. But what isn't balanced is my charge, right? When I look at this magnesium here, it has no charge. So basically the charge on this side is a 0. But when I look over here, this magnesium has a 2 charge. So the charge on this side is +2. So right now, although my elements are balanced, my charges aren't. So how we fix that is we can add electrons, right? So an electron is represented by an E minus. So electrons have a negative charge. So when I'm balancing, I can either choose to add it on this side or I can choose to add it on this side. What's going to determine which side I add it on is how am I going to balance those charges, right? So every electron has one negative charge. So if I need 2 negatives, I would need to use a 2 in front of it for balancing. If I need 3, I would put a 3 in front of it. So if we look back at this magnesium example, right now I have a 0 and I have a +2. So if I were to add electrons on this side, right, usually you guys are pretty good at being like, I know I need 2 electrons, right, because I have 0 and +2, so I need 2 negative things. But generally where you guys struggle a little bit, especially at the beginning, is knowing, should I put it over here or should I put it over here? And we need to think about the fact that every electron has a negative. So if I were to add 2 negatives to this side, that would make the charge over here -2, right, because 0 and 2 negatives is -2. That doesn't equal +2. So I don't want to add the electrons over on this side. I want to add them over on this side, right? If I add them over on this side, and I go +2 electrons, now when I look at it, I have 2 positives from this, and I have 2 negatives from this. And 2 positives and 2 negatives add up to 0. So now I've balanced those charges between the two sides. I've got 0 on this side and 0 on this side. Okay, now we're going to do the same thing with our second half reaction. So we have Br2. There's no charge written here, so that means this has a 0 charge. Here I have 2 Br minus. So because I have the 2 in front, 2 times -1 is -2. So now my charges are 0 and -2. So still need 2 electrons, but in this case, I need to put them over on this side. Okay, and now this results in me having 2 negatives on this side and 2 negatives on this side. So now it's balanced, okay? So things you're going to find. Notice how the electrons in the first half reaction went on this side, and in the second one they went on the opposite side. You should always have them on opposite sides. Okay, not necessarily that the first one's going to go on the right side and the second one's going to go on the left side, but like if I place electrons here in one equation, they have to go on this side in the second one. Or if I had placed them on this side in the first one, they would have to go over here in the second one. Okay, so you should find that those electrons are always on different sides. Okay, and the reason for that is one of our half reactions has to be oxidation and the other one has to be reduction. If they're both on the same side, then they're both oxidation, or if they're both on the other side, they're both reduction. So we said that oxidation is defined as the loss of electrons. So when we look at this, losing electrons means the electrons are going to be on the product side. Okay, so you can add that to your notes if you want, but they are going to be on the product side. Gaining electrons means that they are on the reactant side. Okay, sometimes you guys like to notice that reduction and reaction both start with that R, right? That can help you recognize, oh, my electron's on the reactant side, this is going to be reduction. So from here, I should be able to recognize that out of my 2 half reactions, this one, maybe type up there, is going to be my oxidation half reaction because it lost electrons that are over on this side. And this one is going to be my reduction half reaction because they are on the reactant side and we gained electrons, okay? So they should always be on opposite sides. The other thing you should find, notice how this is a 2 and this is a 2. They should always match up coefficient-wise. Okay, so electrons are on different sides. Coefficient should be the same. If the coefficient isn't the same, so like let's say you do it and you're like, this is a 2 and this is a 4. One of two things has happened. Either you didn't actually balance your equation and that's why your electrons are different, or what potentially has happened is sometimes you guys forget to look at the coefficient that you have here for balancing. And you look at this and you're like, oh, this is a 0 and this is -1. And then you only put 1 electron in and you forget to multiply by that balancing coefficient. So make sure that you are checking for that balancing coefficient as you are going through it, okay? So one of the really important things for you to start being able to recognize is how to write half reactions. And you'll find the first couple of sheets in your booklet are all on how to write half reactions. How to recognize which half reaction is oxidation, which one is reduction. And the next really important piece is to be able to recognize our agents. So in redox, we talk about oxidation half reactions and reduction half reactions. We also talk about oxidizing agents, okay? We abbreviate this to OA, and you're going to find that throughout this entire unit, we're going to say OA and RA. You need to be able to recognize what those are. So an oxidizing agent is the species which oxidizes something else. Okay, so this confuses you guys a little bit because a lot of times you guys go to your half reaction and you're like, oh, here's my oxidation half reaction. Magnesium must be my OA. But if you think about it, the definition of an oxidizing agent is that it oxidizes something else, not that it is oxidized. So what that means is that the reactant in the reduction half reaction is actually your oxidizing agent, right? Because it's what's in your reduction reaction that forces something else to be oxidized. And then if we look at a reducing agent, this is abbreviated to RA. So this is the species that reduces something else. This means it's the reactant in the oxidation half reaction. So to identify your OA and your RA, your first step is basically going to be write your half reactions, figure out which half reaction is oxidation, which one is reduction. Once you know that, you can assign the OA and assign the RA. Okay, they're always the reactant. They're never the product. They're not the electrons. And they get assigned backwards. So what I mean by that is if we go back to this example where we already wrote out our half reactions and we said this was oxidation, because this is the oxidation half reaction, that means that magnesium is going to be my RA. Okay, so the RA is the reactant of the oxidation half reaction. The OA is going to be in my other half reaction. So because this is the reduction half reaction, that's going to have my OA in it. It has to be the reactant, so it's going to be the Br2. So that is going to be my OA. Okay, so let's do one more example just to kind of make sure that you have a couple of different options of seeing this. Okay, so these are questions 1 and 2 out of your booklet. We're going to start with question 2 just because it's a little more straightforward, and then we'll go and do question 1. So first thing we want to do is we want to split this into 2 half reactions. So we're going to look at our elements. We're going to say, okay, we've got iron and iron. So those are going to go into 1 half reaction. And then we've got this zinc and that zinc. So those are going to go into our second half reaction. So we are going to have our Fe turning into that Fe2+. And then we're going to have that zinc 2+, turning into just zinc. Okay, so same thing as we did in the last question. We're going to have a look at how our charges are. So we have no charge on this side, and we have 2+ on this side. So because we have a 0 and +2, we're going to need to add 2 electrons. And we're going to need to add the 2 electrons over to this side. Okay, by putting them on that side, now I have +2 -2. That gives me a sum of 0, which balances the charge on this side, which was a 0. Okay, then we're going to do the same thing with our other half reaction. We're going to have a look at it. This has a 2 charge, so we're going to say that it has +2. The other one has nothing, so we're going to say that it's a 0. Okay, so now when we look at that, we need to add some electrons. Because this is 0 and this is +2, we know we need 2 of them, and we're going to add them over on this side. Okay, they go to this side because 2 negatives and 2 positives add up to 0. So now my charges are balanced between the 2 sides. So next thing I need to do is recognize which one is oxidation and which one is reduction. And I do that by looking at where are the electrons, right? So here, they're over on the product side. That means we lost electrons. Loss of electrons is defined as oxidation. So this must be my oxidation half reaction, which means this one must be my reduction, which it is because the electrons are on the reactant side, which means we gained electrons. So this is the side where we have our reduction. Right, so red, ox, or redox. One's reduction, one's oxidation. Our electrons are on opposite sides. That is a good thing. They are the same number, so we should be good to go. So last thing to do is identify your agents. So because this is the oxidation half reaction, that must mean that iron is my Ra, because remember we said that they are assigned backwards. Because this is my reduction half reaction, that must mean that the zinc ion is my OA. Okay, so it takes a little practice to write those half reactions, get those electrons. Once you placed your electrons, you should be able to identify oxidation and reduction. Then you should be able to recognize Ra and OA. Okay, those are really key pieces for this entire unit. If you can't identify an OA and an Ra, you're going to find that nothing really is going to make sense. So really important, if you finish this and you're like, I have no clue what's happening, that you send me an email and let me know so that we can kind of try to get that sorted for you. because redox is definitely quite an important unit. You will absolutely be doing this in first year university, which is a little different than that organic unit, because organic really is usually a second year course. I know at least when I took first year university, we didn't have any organic in first year. It was all redox, equilibrium, and thermo, and a little bit of like electron modeling, right? So going back to some of those, like, where are electrons placed, what kind of orbitals are they in, that type of thing. So now let's do question 1. So why I save question 1 for later is because every other example we've done either has kind of had this setup or it's had an ionic compound over here. Okay, and water isn't an ionic compound, but we're going to basically treat it as though it is. And you'll see as we go further in the unit, we talk about oxidation numbers, that we get to do some different things when we are in redox that we wouldn't normally do. So what we're going to do is we're going to split this up. So we're going to put the 2H2, right? And that's coming from my reactants over here. And that's going to go with, so here, we're going to say that water is ionic, even though technically it's not, right? So we're going to treat it as though these are hydrogen ions and those are oxygen ions. So if we look at this, for that hydrogen, we have a 2 and a subscript of 2. So we're going to do 2 times 2, which is 4. So we're going to treat this as having 4 hydrogen ions. Okay, then for our oxygen, we're going to say that we have our O2, right? Because that's what we have on the reactant side. And then we're going to say that we have 2 of those oxide ions, so 2O with a 2 minus charge, okay? So, same step, we want to have a look at our charges. There's no charge written in this top corner, so this currently has a charge of 0. We look at our hydrogen, we have 4 positives, right? So 4 times 1 is 4. So on this side, we have plus 4. So in this case, we are going to need 4 electrons. Okay, we need to add them over on this side so that the sum of the charges, right, plus 4 minus 4 is going to equal 0, which is the same that we have over here. When I look at this, right, I've got O2, there's no charge written, so that has a 0 charge. Then for this oxide ion, I have 2 at -2. So 2 times -2 is -4. Okay, so to balance those charges, because I have 0 and -4, I'm going to have to add 4 electrons over on this side, right? So that 0 plus -4 is going to add up to -4, which is the same as this side. So they're on opposite sides. They are also identical numbers, which should always happen. If it's not, something's gone wrong. Now I want to assign oxidation and reduction. So again, my electrons are over here on the product side. That means I've lost them. So this is my oxidation half reaction. Because it's my oxidation half reaction, that must mean that hydrogen is my Ra, because they're opposite to each other. Okay, here for the oxygen, we have those electrons over on the reactant side. That means we gained them. So this is my reduction half reaction. Because this is my reduction half reaction, that must mean that oxygen is my OA. And this is partly why OAs are defined this way, right? Because oxygen, oxidizing, right, kind of go a little bit together. You'll see that some of that is going to continue as we go through. But yeah, so this is going to be my oxidizing agent, and because it is my reduction half reaction. So please make sure you spend some time practicing those first couple of pages in your redox booklet. Really important to make sure that you can write reduction and oxidation half reactions and that you can identify OAs and RAs. If you are struggling with that, you're going to see as soon as you start watching the next video, you're going to be like, whoa, I am lost. I don't know what's happening. So make sure you kind of have that nailed down first, and then you can go ahead and start watching that next video, okay?